So I want to start this deep dive with just a single number, 5 days.
5 days.
Yeah, 5 days. That is approximately how long it used to take to generate
Right.
a decent batch of 50,000 sample images using the previous state-of-the-art AI models.
Right.
And we're not talking about running this on a laptop either. That is on a single A100 GPU, which is a piece of hardware that, costs as much as a decent car.
Oh, yeah, absolutely. And if you're a researcher or a company trying to iterate on a model, 5 days just for one experiment is an eternity. I mean, it's a massive bottleneck.
Exactly.
Yeah.
So for you listening, we've all seen the explosion of AI art lately. But before the research paper we are unpacking today
Yeah.
dropped, high-resolution image synthesis was essentially a game for the elite.
Definitely. You needed a supercomputer, basically.
Right, or at least a budget that could burn through electricity like a small village. But today's deep dive is on a paper called High-Resolution Image Synthesis with Latent Diffusion Models.
Which is a bit of a mouthful, but it really is the research that changed the game.
Yes. It really did. And it was a collaboration between researchers at Ludwig-Maximilian University of Munich, IWR Heidelberg, and the team at Runway ML.
Right, and their mission here was simple but incredibly ambitious. They wanted to keep the high quality of the images but stop the dependency on supercomputers.
They call it democratizing image generation. And, usually when tech companies say democratizing, they just mean we found a way to make it cheaper for us to run in our data centers.
Yeah, exactly.
But this one actually feels different. Does this actually help the average user?
In this case, yeah, it actually does. By fundamentally changing the architecture, specifically where the AI actually does its thinking, they made it possible for these massive models to run on consumer hardware.
Oh, yeah.
So if you've ever run Stable Diffusion on your own gaming PC, for instance, you basically have this specific paper to thank for that.
Okay, so let's get right into the weeds here. To really appreciate the solution they came up with, I think we first have to understand why the old way was so terribly inefficient.
Right, so we are talking about diffusion models here, or DMs.
Yeah, but before this paper, we had things like GANs, right? Generative adversarial networks. And they were fast, but from what I understand, they were notoriously unstable to train.
Very unstable. They suffered from this thing called mode collapse, where the model would just figure out how to make one good image and then just keep generating the same few things over and over again.
So GANs were kind of like a really fast but totally unreliable artist.
That's a good way to put it. So then the field moved to diffusion models. DMs were much more stable.
Because they gradually denoise things, right?
Exactly. They take a normally distributed variable, basically a block of pure static noise, and they learn the data distribution by gradually denoising it, reversing the process step by step until an image appears.
Kind of like sculpting. You start with this messy block of noise and you just chip away until you find the final image.
Right, but the big bottleneck was where they were doing that chipping. The older DMs were operating directly in what we call pixel space.
Pixel space. Let's break that down for the listener.
Sure, so digital images obviously contain millions of individual pixels, especially high-resolution ones. And most of those bits correspond to high-frequency data.
Which means what exactly?
It means imperceptible details, tiny shifts in color or light that your eye barely even registers. But in a standard diffusion model, the neural network has to evaluate and optimize every single one of those millions of pixels at every single step.
So it's optimizing things we can't even really see.
Exactly. Which makes the optimization incredibly expensive and agonizingly slow, like you mentioned earlier. That's why producing those 50,000 samples could take 5 days on an A100.
It really feels to me like trying to write a summary of a book by analyzing the exact ink density of every single letter on the page, rather than just, reading the plot.
That is the perfect analogy. The models were spending all their energy computing the ink usage instead of focusing on the actual meaning of the image.
Okay, so what's the fix? The paper proposes latent diffusion models, or LDMs. I'm guessing the title gives it away, right? We are moving from pixel space to latent space.
Exactly. We're departing pixel space entirely.
But latent space always sounds like Star Trek technobabble to me. What is actually happening under the hood there?
So the authors propose a two-stage approach. They completely separate the training into two phases. Stage one is what they call perceptual compression.
Compression like zipping a file or saving a JPEG?
Conceptually similar, yeah, but this is learned compression. They train an autoencoder. This autoencoder has two parts. An encoder, which we can call E, it takes that massive pixel image and compresses it down into a much lower dimensional space.
And that compressed space is the latent space.
Yes. They denote that latent space as Z in the paper. Then there is a decoder D, which takes that compressed Z representation and reconstructs the full image from it.
But hang on, if we compress the image, aren't we just losing a ton of quality? Like if I compress a photo too much, it gets all blocky and blurry. How do they get a masterpiece back from that?
That's the million-dollar question. A standard compression algorithm might just blur things.
Yeah.
Yeah. But this specific autoencoder is trained very carefully to avoid that.
How so?
They train it using a combination of a perceptual loss function and a patch-based adversarial objective.
Okay, you're going to have to translate that for me.
Fair enough. It basically means the encoder is heavily penalized during training if the image it reconstructs looks blurry or fake. It's mathematically forced to keep the important texture and sharpness encoded in that tiny latent space.
So it's kind of packing the essence of those imperceptible details into the latent code without actually saving the raw pixels.
Exactly. It throws out the junk, but keeps the perceptual essence.
Okay, but I saw in the paper they also talked about regularizing this latent space. They mentioned KL regularization and VQ regularization. Why do they need to regularize it at all?
Because if you don't regularize it, the latent space becomes totally chaotic. It develops high variance.
Meaning what?
Meaning 2 points that are mathematically right next to each other in the latent space could decode into completely wildly different images. You want a smooth, predictable map.
Ah,
So KL regularization pushes the latent codes towards a standard normal distribution, just keeping it tidy. And VQ, which stands for vector quantization, creates a discrete codebook of latent components.
so it's kind of like organizing a library. So all the science fiction books are on one shelf and biographies are on another, rather than just throwing everything in a massive pile on the floor.
Exactly. That structure is what allows the second stage to actually work.
Right, stage 2. This is where the semantic compression happens, the actual diffusion part.
Yes, this is the breakthrough. Instead of running that massive, expensive noise chipping sequence on millions of pixels, they run the diffusion process entirely inside that compressed latent space Z,
Which is way smaller.
exponentially smaller. And because all that high-frequency perceptual noise was abstracted away by the autoencoder in stage 1, the diffusion model doesn't have to worry about it.
You can just focus on the plot of the image, to use our earlier analogy.
Exactly. It focuses purely on the semantic bits, the shapes, the objects, the overall meaning.
So all the heavy lifting computation happens in this tiny, efficient, latent room.
Right. And then once the diffusion model generates a clean semantic latent code, it hands that code over to the decoder D.
And the decoder just blows it back up into pixel space.
Yes. It reconstructs the final image.
That is so clever. But there has to be a trade-off, right? You can't compress things infinitely. The paper talks about this downsampling factor, right?
Well,
the factor F.
They do. They ran a ton of experiments with different factors. They tested F equals 1, 2, 4, 8, 16, and 32.
And I'm guessing F equals 1 is just regular pixel space?
Yes, F1 means no compression. And as we know, that's way too slow. But the interesting finding was that F32, which is the most extreme compression, was actually a failure.
Really? Why is that? I would have assumed more compression means a faster model, which would be better.
It was definitely faster, but the quality just stagnated. It plateaued.
Because it lost too much information.
Exactly. When you compress by a factor of 32, you lose too much spatial structure. These are convolutional models. They rely heavily on spatial adjacency. They need to know that this cluster of pixels is physically next to that cluster of pixels. At F32, that entire geographic map is basically lost.
So it essentially forgets where things are supposed to be in the image. So what was the sweet spot then?
The paper found a Goldilocks zone at factors F4 and F8.
Huh?
Those factors offered the perfect balance. They gave massive efficiency gains, but still retained enough of that spatial map to allow for high-fidelity reconstructions.
So we have this super fast, highly efficient engine now. But an engine is pretty useless if you can't steer it.
Very true.
The most magical part of this tech for a lot of people is that you can just type a prompt. Like, I don't know, a painting of a squirrel eating a burger, and it just makes it.
Right.
How does the text actually get into the image generation process?
That brings us to the architecture they used, specifically the cross-attention mechanism.
I see this word attention everywhere in AI papers.
It's crucial. The backbone of the model here is a UNet. It's a type of neural network that's actually been used a lot in medical imaging.
Okay.
But to make the UNet actually listen to your text prompts, they modified it by injecting these cross-attention layers right into the architecture.
How does that actually work, though? Are they just mathematically gluing the text to the image?
It's a bit more elegant than that. They use a domain-specific encoder. The paper mentions using the BERT tokenizer and transformer encoders.
So that processes the language part.
Yes.
Yep.
It takes your prompt about the squirrel and turns it into an intermediate representation. Then inside the UNet, they map everything to query, key, and value representations.
Okay, you're getting a bit deep into the math there. Queries, keys, values. Give me an analogy for that.
Fair enough. Think of the UNet as a painter standing at a canvas. The query is the painter looking at a very specific spot on the canvas and asking, what should I paint right here? The keys and values come from your text prompt. The text prompt holds the answer. It essentially says, at this spot, you should paint brown fur because we are painting a squirrel.
So every single step of that denoising process, the visual part is constantly querying the text part to make sure it's staying on track.
Exactly. The cross-attention layers calculate the correlation between the visual features in the UNet and the text features from your prompt. It allows the language to spatially guide what gets drawn.
That makes total sense. And the paper emphasizes that this is multimodal, right? It's not just limited to text to image.
Not at all. Because this cross-attention interface is so flexible, you can plug almost anything into that domain-specific encoder.
Like what else?
You can feed it semantic layout maps, bounding boxes, or even other images to guide the generation. It's basically a Swiss Army knife for image synthesis.
It really is. Okay, let's pivot and talk about the actual results because, AI papers always love to claim state-of-the-art performance, but usually there's a catch.
There usually is.
Did this model actually beat the supercomputer models in pure quality?
It absolutely did, and it did it while requiring a fraction of the compute. They measured this using FID scores.
That's fresh 8 inception distance, right? And lower is better.
Yes, lower FID means the generated images are statistically much closer to real, actual photographs.
Got it.
For unconditional generation, meaning just asking the model to dream up images without a specific prompt, they hit new state-of-the-art FID scores on datasets like Celeba HQ, which is high-res faces, and LSU in churches.
Just generating photorealistic faces and buildings out of thin air.
Exactly. But honestly, what's more impressive than just the raw scores is the versatility we mentioned. They tested it on super resolution tasks, too.
Super resolution, like the enhance button from those old cop shows.
Exactly like that. Taking a low-resolution pixelated image and mathematically upscaling it. The paper compares their LDM SR model against a state-of-the-art method called SR3.
And SR3 operates in the old pixel space, right? How did they compare?
This is where the results get really nuanced and fascinating.
Yep.
The pixel space SR3 model actually had slightly better scores when it came to fine structures.
Meaning what, exactly?
Meaning the absolute geometric precision of the lines.
Oh, okay.
But when they did human evaluation, people strongly preferred the images generated by the LDM.
Really? Why is that? If the other one was more geometrically precise?
Because LDM produced vastly superior textures. It wasn't just blindly sharpening the existing blurry lines. It was synthesizing highly realistic, plausible textures.
Like skin pores or the weave of a fabric.
Exactly. Details that simply did not exist in the low-resolution original.
So it was actually hallucinating reality better than the other model?
In a way, yes. It prioritized perceptual quality, what looks real to the human eye, over pixel-perfect mathematical accuracy.
That is wild. And then there's in-painting. This is the feature I think I use the most, honestly. When you mask out a region of an image and tell the AI to fill the gap.
Yes, it's a huge use case.
How did LDM do there compared to specialized in-painting models?
They ran it against a highly specialized model called Llama, and the biggest difference they found was in the diversity of the output.
Define diversity in this context. What do you mean by that?
Well, traditional in-painters like Llama tend to play it very safe. If you mask out a park bench in a photo, Llama will likely just blur the surrounding grass and BERT to fill the hole.
It just averages out the background.
Right. It's essentially a smart clone stamp tool.
Yep.
But LDM, because it truly understands semantic concepts through that latent space, doesn't just clone, it invents. It might put a rock there or a puddle or a fallen branch.
It generates distinct, realistic alternatives instead of just smoothing over the whole.
Exactly. It improves the overall image quality because it acts more like a creative partner than just a patch tool.
Okay, and there was one more big win mentioned in the paper. Convolutional sampling.
Yes, this is a massive advantage of their architecture.
This is the part about generating huge images, right?
Right. The LDM is fully convolutional, and it was trained on relatively small images, mostly 256 by 256 pixels.
Just tiny.
But because of the architecture, you can apply it in a convolutional fashion to an image of virtually any size.
So you can generate megapixel landscapes using a model that only ever studied tiny little squares.
Precisely.
That seems totally counterintuitive to me. If it only ever saw small squares, how does it know how to compose a massive, consistent panorama?
Because the underlying concept of a texture or a specific object is essentially local. A patch of grass looks like grass whether it's in a tiny photo or a massive mural. The model is able to stitch these local concepts together seamlessly across a massive canvas.
That is incredible. But I have to play devil's advocate for a minute here.
Go for it.
We've established that this tech is faster, it's cheaper, and it can run locally on consumer hardware. The paper puts a massive emphasis on this democratization being a positive thing.
Yes.
But is it actually purely a good thing? Because it feels like a double-edged sword.
It absolutely is a double-edged sword, and to their credit, the authors have an entire section dedicated to societal impact.
Usually those sections in tech papers are just lip service, though.
Yeah,
Did they actually engage with the real risks of open sourcing this?
they did. They were remarkably direct about it, actually. They explicitly link the efficiency of their model directly to the potential for misuse.
How so?
Well, think about it. When a massive model requires a data center supercomputer, it's centralized. A big tech company controls the API,
Right.
which means they can put strict safety filters on it. They can stop you from generating violent imagery or deepfakes because everything runs through their servers.
But if I can download LDM and run it on my own rig in my basement offline.
Exactly. There is no API filter. The democratization of the technology fundamentally means the decentralization of control.
Wow.
The authors explicitly state that making these models accessible makes it much easier to generate manipulated data misinformation and spam.
And they specifically pointed out the risk of deepfakes, right?
Yes, they did. And importantly, they noted the disproportionate impact this has. The paper explicitly points out that women are overwhelmingly the targets of non-consensual deepfake imagery.
So by radically lowering the computational barrier to entry, they are simultaneously lowering the barrier for harassment and abuse.
That is the reality of this situation, yes.
It's the classic open source dilemma. You can't give a powerful brush to the artist without also handing it to the trolls.
Very true. And on top of the deliberate misuse, there are also systemic issues with the data itself.
Because these models are trained by scraping billions of images off the open internet.
Right. And deep learning modules, by their very nature, tend to reproduce or even exacerbate the biases already present in that training data.
Right. So if the internet historically depicts, I don't know, CEOs as mostly men and assistants as mostly women, the model heavily encodes that correlation into its latent space.
Exactly. The AI doesn't understand social progress or fairness. It only understands the statistical frequency of the data it was fed.
So by compressing the internet into a highly efficient latent space, we are essentially compressing all of the internet's prejudices right along with it.
Precisely. And the paper also raises concerns about data privacy, specifically the issue of memorization.
What does that mean in this context?
Sometimes, though, it is rare, these massive models can actually regurgitate exact pieces of their training data.
Oh, wow.
So if sensitive personal information or copyrighted material was scraped and included in the dataset, the model might accidentally reveal it during generation.
That is definitely a privacy nightmare waiting to happen. It really shows that this tool isn't just a purely creative engine, it's a mirror.
A funhouse mirror, maybe? It definitely reflects society back at us, but with all its distortions amplified.
Okay, so let's zoom out and summarize this for the listener. What is the ultimate takeaway from this research?
The big aha moment is that we finally stopped trying to paint every individual pixel. We shifted the computational heavy lifting to a compressed latent space.
We started manipulating the semantic concepts rather than doing brute force calculations of light rays.
Exactly. This paper proved that you don't need to simulate physics to generate a realistic photo. You just need to efficiently understand the distribution of the data.
It really feels like we've crossed a fundamental threshold here. Like before this paper, a photograph was essentially physical proof that light bounced off an object and hit a sensor.
Right.
Now, a highly realistic photograph is just a probability distribution that won a mathematical dice roll.
That is a very haunting but accurate way to put it.
Well, I want to leave everyone listening with a final thought on that upscaling capability we discussed earlier.
The super resolution part.
Yeah. We talk about how the model prioritizes perceptual quality over exact pixel accuracy, how it hallucinates textures and eyelashes and brickwork that look incredibly real but technically weren't there in the original low-res data.
Right, it makes the image look more real to us than the raw data actually supports.
Exactly. So as these latent diffusion tools become the standard operating systems in our phones and our cameras, and they already are, we are stepping into a world where the photos we take are constantly being quietly corrected.
Corrected by an AI statistical idea of what the world should look like.
Right. If the algorithm decides that the sky should be a slightly bluer blue, or that a face should have fewer wrinkles or more symmetrical lighting, that hallucination is what gets saved to your hard drive.
So we are slowly archiving an interpretation of reality rather than a strict record of it.
Yes. We are replacing our actual messy past with a statistically optimized hallucination. At what point does a photograph stop being a memory and start being a suggestion?
And the scary part is we might not even notice the transition happening.
Definitely something for you to think about the next time you tap that magic editor button on your phone. Huge thanks to the teams at LMU, Munich, Heidelberg, and Runway ML for this incredible research.
It is a truly masterful piece of engineering.
It really is. And thank you to everyone listening for taking this deep dive with us today.
Catch you next time.